Okay, and on to the square of the correlation. So if we take the correlation and we square it, we simply call it r squared. And by definition, it is the fraction of the variation in the values of y that is explained by the least squares regression of y on x. So that is the variation in the numerator. It's the variation of the y hats. Those are the predicted values along the regression line as x changes, and then divided by the total variation in observed values of y, so how they all differ. And to get that, we have an example here. Let's suppose r equals 0.98, just like in our example at the end of chapter 4. And to get r squared, we simply square it, and we get here 0.9604 or 96%. Most often, r squared is expressed as a percentage between 0 and 100%, so 96%. So if r is a value between -1 and 1, then r squared, once we square that value, it must be a number between 0 and 1. And that's why we can express it as a percent. We use r squared to assess the fit of the regression line. So the closer r squared is to 1, then we have a better model. So this is saying 96%, which would be phenomenal. So if it's close to 0, then the fit is not as good as it would be if it's closer to 100%. And we need to remember it must be the linear relationship. All of these tools are for linear relationships only. Okay, so r squared near 0 means a weak linear relationship. R squared near 1 means a strong linear relationship. All right, and note that with r squared, we do lose information about the direction. We cannot know, if we only know r squared, we could get the correlation by taking the square root, but it's plus or minus the square root. And we don't know whether it's plus or minus, so we need to know what the slope is. And if the slope is negative, then the correlation is negative. If the slope is positive, then the correlation is positive. So we could have y equals a plus bx, then that would mean we have a positive correlation. We could have y hat equals a subtract bx, then that means the slope is negative right here. And then we have a negative r. So r would be negative instead of positive. So we always look at the least squares regression line or simply the value of the slope. Moving on to the residuals. So the residuals has a little formula, y subtract y hat. So it's the vertical distances, like I've drawn here, from the observed y, from the xy pair, subtract y hat. And when we do that, we can get that vertical distance. And the sum of all of them must equal 0. So the observed value is from the data, and the y hat is from the line. And the sum, here's what I was saying, the sum of all the residuals has to equal 0. And if the sum is 0, then the mean of the residuals also has to be 0. So we always look at the residual plots. And that's what we have here on this slide, is the residual plot. So you plot the values of the residuals against the explanatory variable. And we can see that there is an outlier here. And it's pretty empty on the right side of this plot. So this side is not as much data as the other side. And we want it to be really random scatter about the 0. And 0's here with the red line. So 0, we have some residuals that are above 0. Those would be the points that are above the regression line. And we would have some residuals that are negative, which are below 0, which would be below the regression line. And that's good. We want to have random scatter. This is good. It means we have a good model. If there is a pattern in the residual plot, such as a linear pattern, then we don't have probably a good model, and we probably wouldn't want to trust the predictions and use that model. So we would want to use other tools for nonlinear regression, which is beyond the scope of the course. So we look for those things. That's why we always check the residual plots and check to make sure that we do have random scatter. Influential observations. So we know what an outlier looks like. This is an outlier here. And we all outliers, well, actually it's the other way around. All influential observations are outliers, but not all outliers are influential. So an outlier is, or an observation is influential if, or a statistical calculation, if removing it would remarkably change the result of the calculation. So if the line moves quite a bit, then it's an influential observation. And points are outliers in either X or Y direction, so vertical or horizontal of a scatter plot, and are often influential for the correlation, as we'll see in the next slide. Points that are outliers in the X direction are often influential for the least squares regression line. So you want to just sort of cover that. You can cover this and just imagine that the line would change from that red line to what I've drawn here is in the purple. So it would be definitely an influential observation. That's subject 2. And there it is again. And we can see the value of the correlation R has been calculated. From using all the data, we get 0.181. And when we remove the subject 2, right here, if we remove that point, we get a correlation of negative 0.043. So much more weak. Not only did it go from positive to negative, but it also became much weaker correlation. So just by having one outlier in or out of the data set can have that much of an effect on the correlation and the regression line as well. Some cautions about correlation and regression. Remember that it's only for linear relationships for this course that we're taking. Just all the tools in these chapters, chapter 4 and 5, are for linear only. So we want to keep that in mind. They're not resistant, so even if one outlier can actually change the least squares regression line and the value of the correlation. We also want to be aware of ecological correlation. I'll show you in the next slide what that means. And also beware of extrapolation. I will also show you what that means in the next slide. And lurking variables. These have an important effect on the relationship. So those are variables that are not included in the study, outside factors that could be influencing the correlation. So another big takeaway is the correlation does not imply causation. So no matter how strong the correlation is, it does not mean that we have causation. It does not mean that X causes Y. All right. Ecological correlation is right here, showing in the left graph. We have each group here I have circled in orange. Those are groups of points. On the horizontal axis, our X is education, and we have wage on the vertical. And so as education increases, so does the wage. We have an outlier up here, but we have lots of individual people and their education and their wage. plotted here, and the R is 0.394. That's the correlation. Now, if we take the average of each of those groups, so for 6 years, 7 years, 8 years, 9 years that I've circled in orange, and we plot them only in the plot in the right, then we have a much stronger correlation. And it is calculated to be 0.952. So quite a difference there. So we want to be careful. Is the data, you can ask yourself, is the data individuals or is it based on averages? Also beware of extrapolation. You only want to make predictions with your line, the squares regression line, based on the data within. So you wouldn't want to make any predictions that go outside the data. So nothing lower than the lowest point of X and nothing higher than the highest point of X. So this is height of Sarah, and it's her age as well against her age. So we have, can you predict her height at age 42? If we put in age 42 right here, yes, this is safe. We can easily predict that value. The y hat would be right here, output. So the line is actually y hat equals a plus bx, and the output would be equal to that output. If you put in 42, you get an output of whatever you get based on the line. And can you predict her height, though, at age 30, which would be 360 months, which would be way, way, way past the page? And the answer is no, because at that point, you're going outside the data, the original data, and that is called extrapolation. You can see it further here mathematically and also with the picture that we know that as we grow, we eventually start to stay the same. We don't keep growing and growing and growing. So that's why it's an example that shows if you predict beyond, you're going to keep it linear, which is incorrect, right? Because we know it does that. But with some other items, we may not know what happens outside the data range. With height, it's obvious, we know, but with other data, we might not. So they're showing here y hat equals 71.95 plus, so that means a positive slope there, 0.383. We plug in 42 and we get 98. And predicted height at age 30 years would be 209.8, and that means she would be predicted to be 6 feet 10.5 inches tall at age 30. So you can, it's a way to illustrate the extrapolation and why we should not do that. And beware of lurking variables. And so a lurking variable, as I mentioned, is a variable not included in the study design that does have an effect on the variable studied. And there's two examples here where you can think about what could be the lurking variables. The first one is strong. Suppose there's a strong positive association between the number of firefighters at a fire site and the amount of damage a fire does. So a lurking variable could be the size of the fire, and the location and so forth. The negative association between moderate amounts of wine drinking and death rates from heart disease in developed nations. A lurking variable could be, well, it could already be less death rates from heart disease just because it's in a developed nation because of better healthcare, better lifestyles, and taking care of themselves. And it's not necessarily the moderate amounts of wine. And correlation does not imply causation, right? Even the most strong correlations may not correspond to a real causal relationship. So that does not mean that X actually causes changes in Y. And correlation may be explained by a lurking variable. Okay, so we talked about this, social relationships and health. Does lack of social relationship cause people to become ill? Right, there's a strong correlation. Or are unhealthy people less likely than others to establish and maintain social relationships? Or is there some other factor that predisposes people both to have lower social activity and to become ill? So these are things to keep in mind. It's external, outside causes, right? So only a proper experiment can show causation, and we will look at experiments, experiment designs in a future chapter of the course. All right. And I was showing here on this page two different ways to write that formula. So there's one that's the slope formula, and it can be rewritten as as we discussed, right? You just have to watch the indices, what the subscripts, sorry, the subscripts for X and Y. And that brings us to our example. We have time spent X and Y, online sales. We calculated at the end of chapter 4 for the example, all of these summary statistics. And then from those summary statistics, we can calculate the slope. We ended up with 0.52. And for the intercept, we ended up with 75.16. Okay. And then from there, we were able to put it all together. Y hat equals 75.16 plus, and plus means the positive slope, the plus sign. If it's negative there, that would mean a negative slope. And so it's 0.52 times X, and X in this case is the time spent. And so part B says use the least squares regression line to find X bar. That is our average minutes, 62. So Y bar or X bar is 62. We sub that in to the equation. So Y hat equals 75.16 plus 0.52 times, we're subbing that into the equation 62, and we get 107.4, which is equal to our Y bar. And that is a way to know if you've calculated the least squares regression line accurately or not. So we have the proper A slope and A intercept and B slope. All right, and the part C wants us to sub in 90 minutes, make a prediction using 90 minutes, so that would be Y hat equals 75.16 plus 0.52 multiplied by 90, that gives us $121.96. And finally, part D says, what is the residual if a customer in part C actually spent $115? So our residual formula is Y minus Y hat, which is going to be Y is 115 given by the question, subtract $121.96 that we got from part C, and the leftover is 6.1 or 6.96, which means that our prediction was overestimated by $6.96.